Picture a speck of reflected sunlight drifting inward through the space between Neptune and Saturn. At first, nothing about it seems impossible. But then the measurements begin to arrive. The velocity shows a drift, subtle but persistent, that orbital mechanics cannot fully account for. Spectral lines flicker in and out of confidence thresholds, too faint to confirm, too consistent to dismiss. Brightness does not scale cleanly with distance. It rises and falls in patterns that resist solar geometry. And in high resolution, frames separated by weeks, a structural asymmetry appears on one side of the nucleus, then vanishes, then reappears elsewhere. The data is not noisy. The instruments are not confused. The only variable left to question is the model itself. Is this an unfamiliar natural process unfolding at the edge of detectability, or the quiet breakdown of everything we assume about objects like this? It begins with something almost invisible. On a winter night in early 2024, automated survey telescopes, scanning the outer solar system, registered a faint point of light, moving against the fixed stars. The signature was unremarkable at first. A slow drift, typical of distant asteroids or long-period comets making their way sunward. But within days, astrometric refinement revealed something unexpected. The object was not bound to the sun. Its orbit was hyperbolic. It had come from beyond. The designation was assigned quickly: 3A Atlas, the third confirmed interstellar interloper, the third visitor to pass through our solar system from the vast darkness between stars. But this time, the measurements would not settle. In those first weeks, observers noted details that did not align cleanly with expectation. The apparent velocity showed minor deviations from the predicted trajectory, small enough to attribute to measurement uncertainty, but consistent enough to warrant additional observation. Spectroscopic attempts returned ambiguous results: possible emission features near ultraviolet wavelengths, faint absorption bands that matched no clean reference, and a continuum that seemed flatter than standard cometary dust models would predict. Photometry revealed brightness variations that changed faster than solar distance alone could explain, and imaging sequences captured a coma structure that appeared asymmetric in some frames and nearly symmetric in others, with no obvious correlation to rotation or viewing angle. None of these observations, taken individually, would constitute a crisis. Comets are complex. Small bodies exhibit variability. Noise is expected at the limits of detection, but the pattern was different. The inconsistencies were not random. They accumulated in a way that suggested something fundamental was missing from the interpretation. And so the question formed quietly in observatories and data centers around the world. Are we witnessing a natural process we have never encountered at this resolution? Or are our models being tested by something they were never designed to describe? If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. The path through space is not a guess. It is a calculation, constrained by geometry and time. 3A Atlas was first detected at a heliocentric distance of approximately 7.8 astronomical units, just beyond the orbit of Jupiter, inbound toward the inner solar system. Orbital elements were derived from position measurements taken over successive nights, corrected for parallax and atmospheric distortion, then refined through iterative least squares fitting. The eccentricity emerged above unity, 1.032, confirming a hyperbolic trajectory. The orbital inclination measured 41.7 degrees relative to the ecliptic plane, indicating an approach from well above the plane of the planets. And the hyperbolic excess velocity, the speed at which the object would escape the sun's influence once free of its gravity, was calculated at 3.2 kilometers per second. This placed 3IS within a known class of interstellar objects, slower than Oumuamua, which departed at nearly twice that speed, but faster than any gravitationally bound comet originating from the Oort cloud. Backtracking the orbit revealed its origin. The object had entered the solar system from the direction of Canes Venatici, a region of the northern celestial hemisphere devoid of bright stars, but rich in distant galaxies. Its inbound velocity vector pointed toward no obvious stellar system within 100 light-years. It had drifted for millions of years through the space between suns, carried by whatever momentum it possessed when it was last perturbed by gravity, or ejected from a distant planetary system. The outbound trajectory was equally well defined. After passing perihelion, its closest approach to the Sun, at roughly 2.10, just inside the orbit of Mars, 3 Atlas would arc back out through the outer solar system, passing within gravitational range of Jupiter before departing toward the constellation Pegasus. Its departure velocity would carry it back into interstellar space, where it would continue for another eon, unobserved and untracked, until chance brought it near another star. This much was certain. The path was measurable. The geometry was sound. But the behavior along that path, that was where certainty began to erode. When an object defies easy explanation, the instinct of science is to multiply the instruments trained upon it. 3 Atlas became a target of coordinated international observation within weeks of its discovery. Pan-STARRS, the survey telescope in Hawaii that first flagged the object, continued nightly monitoring to refine its ephemeris. Hubble Space Telescope was tasked with high-resolution imaging to resolve the nucleus and measure coma expansion rates. The James Webb Space Telescope turned its infrared instruments toward the object, searching for thermal emission signatures and spectral features invisible to optical telescopes. Subaru's wide-field imager captured deep exposures to trace the faint outer envelope of dust. ALMA, the radio interferometer array in Chile, probed for molecular emissions, carbon monoxide, methanol, hydrogen cyanide, that would betray the composition of sublimating ices. Gaia, the European space astrometry mission, contributed precise positional data, cross-referenced against stellar parallax, to eliminate systematic drift. Amateur observers with CCD-equipped telescopes added hundreds of data points, independent of professional networks, providing redundancy and temporal coverage that no single facility could achieve alone. Every dataset was scrutinized. FITS files were re-reduced from raw frames. Flat field corrections were recalibrated. Bias frames were stacked and subtracted. Signal-to-noise ratios were recalculated at multiple aperture sizes. Cosmic ray hits were masked. Stellar contamination was modeled and removed. And the anomalies persisted. Different instruments, observing at different wavelengths, from different locations, under different atmospheric conditions, returned results that agreed on the object's position and brightness, but disagreed on finer details. Hubble captured a jet-like structure extending westward from the nucleus in one observation, but follow-up imaging 2 weeks later showed symmetry. JGUST detected a faint infrared excess that suggested dust grains warmer than solar heating alone would predict. ALMA found weak emission lines consistent with water and carbon monoxide, but at intensities lower than expected for an object producing a visible coma. The data converged on one conclusion. The anomalies were not artifacts of instrumentation. They were properties of the object itself. Physics offers predictions. It tells us what should happen to a small icy body entering the inner solar system from interstellar space. As 3I Atlas approached the Sun, solar radiation should have begun to heat its surface. Volatile ices, water, carbon dioxide, carbon monoxide, should have transitioned from solid to gas, carrying dust particles with them in a process called sublimation. This gas and dust should have formed a coma, a diffuse cloud surrounding the nucleus, expanding outward at speeds determined by the molecular weight of the gases and the temperature of the surface. Jets, driven by localized heating on the rotating nucleus, should have produced structures in the coma: fans, spirals, shells, visible in time series imaging. The spectroscopic signature should have been predictable. Emission lines from hydroxyl radicals, formed when water molecules are broken apart by ultraviolet sunlight. Reflected sunlight scattered by dust, with a spectral slope determined by particle size and composition. Absorption bands in the near infrared, indicating the presence of organic molecules or silicate grains. Albedo, the fraction of sunlight reflected by the surface, should have remained relatively constant unless the surface composition changed through sublimation or dust mantling. Mass loss rates should have increased with decreasing heliocentric distance, following an inverse square relationship with solar flux. Non-gravitational forces should have appeared. The recoil from jetting gases acting like a weak rocket engine, would subtly alter the object's trajectory. All of this is standard. It is textbook cometary physics. It is what we have observed in hundreds of comets over decades of study. And yet, with 3I Atlas, the measurements drifted from the predictions. The first sign of trouble came from astrometry. Position measurements, when compared against the best fit orbit, showed residuals, small differences between observed and predicted positions that exceeded the expected error budget. These residuals were not random. They accumulated in a consistent direction, suggesting the object was accelerating slightly faster than gravity alone would allow. Non-gravitational acceleration is not unusual for comets. Outgassing produces thrust. But the magnitude of the acceleration observed in 3A Atlas was larger than models predicted based on its brightness and estimated size. Either the object was producing more gas than its coma suggested, or the gas was being expelled in a geometry that concentrated thrust more efficiently than isotropic sublimation would allow. Then came the tail orientation problem. Dust tails point away from the sun, pushed by radiation pressure. Gas tails composed of ions are swept back by the solar wind and point along the direction of the object's motion relative to the sun. These geometries are well understood. But in several imaging sequences, the tail structure of 3E Atlas appeared to deviate from the expected orientation by several degrees. The deviations were intermittent. Sometimes the tail aligned perfectly, other times it did not. No single explanation for rotation or viewing angle resolved all cases. The brightness curve presented its own puzzle. Photometric data showed variations in apparent magnitude that could not be fully explained by changing distance or phase angle. The object brightened and dimmed on timescales of hours to days, suggesting either rapid changes in surface activity or rotation-driven changes in cross-sectional area. But attempts to fit a periodic light curve, indicative of a rotating irregularly shaped nucleus, failed to produce a stable solution. The periodicity seemed to shift, or the amplitude changed unpredictably, or both. Multiple teams attempted to reconcile the data. One group proposed a highly elongated nucleus with variable dust production rates tied to latitude. Another suggested a binary system, two objects orbiting each other, each contributing differently to the total brightness. A third invoked a porous, fractal structure that altered its scattering properties as material sublimated from the interior. None of these models fit all the data simultaneously. Adjusting parameters to match the photometry broke the fit to the astrometry. Correcting the tail geometry introduced inconsistencies in the spectroscopy. Each solution solved one problem while creating another. When established models fray, the search for explanations expands outward, carefully, testing the boundaries of what is known before venturing into what is speculative. The first line of inquiry focused on asymmetry. If the nucleus of 3E Atlas was irregularly shaped, or if its surface composition was patchy, areas of pure ice next to areas covered in dust, then heating would be non-uniform. Active regions would produce jets at specific latitudes and longitudes, varying in intensity as the object rotated. This could explain both the brightness fluctuations and the non-gravitational acceleration, if the jets were preferentially directed in one hemisphere. Modeling efforts incorporated complex surface thermophysics, heat diffusion into subsurface layers, phase transitions at depth, and the insulating effects of a porous dust mantle. Some models introduced exotic ices, nitrogen, methane, or even more volatile species like carbon monoxide ice, that sublime at greater distances from the sun than water, potentially activating the object earlier and more unpredictably than standard cometary models would suggest. Another avenue explored dust properties. If the dust grains were not solid, compact particles, but instead fractal aggregates, loosely bound clusters of smaller grains, then their interaction with sunlight would differ significantly. Fractal dust scatters light more efficiently at certain wavelengths and experiences different radiation pressure forces, altering both the brightness and the dynamics of the tail. This could introduce variability that appeared independent of heliocentric distance. More speculative ideas emerged cautiously. Could the object be a rubble pile, a loosely bound collection of fragments rather than a single cohesive nucleus? If so, differential forces acting on individual components could produce apparent accelerations or rotational instability. Could there be internal reservoirs of gas trapped beneath a crust that episodically vent through fractures, producing bursts of activity uncorrelated with solar heating? At the edge of conventional explanation, some researchers considered models that strained against the boundaries of known physics without crossing into the implausible. Could 3I Atlas be a disaggregating object, slowly breaking apart under thermal stress, releasing material in ways that mimicked but did not precisely match standard outgassing? Could electrostatic forces, generated by solar-wind interaction, play an unanticipated role in dust-grain dynamics? One hypothesis, rarely voiced in formal papers but discussed in conference hallways, asked whether 3I Atlas could be something other than a single monolithic object. Could it be a swarm, a distributed collection of smaller bodies traveling in close formation, appearing as a single entity at low resolution? Such a configuration would present a constantly shifting cross-section, variable reflectivity, and apparent acceleration that did not trace to any single propulsion mechanism. The distinction between natural and non-natural was kept explicit. No model invoked intent. No explanation required technology. But the boundary of what counted as natural cometary behavior was being tested, and the object itself seemed indifferent to whether observers were comfortable with the results. The future is not a mystery. It is a timeline, with calculable events and measurable consequences. 3I Atlas will continue its inbound journey over the coming months, reaching perihelion in mid-2025. At closest approach, solar heating will intensify, and if the object behaves according to any variant of cometary physics, activity should increase. Dust production rates should rise. Gas emission should strengthen. The coma should expand, and the tail should grow more prominent. But the approach to perihelion offers more than passive observation. It offers tests. As 3I Atlas descends through 4O, then 3O, then closer, its brightness should follow a predictable relationship with solar distance. Deviations from this relationship will constrain models of surface activity and dust composition. Spectroscopy, conducted at regular intervals, will reveal whether new volatiles begin to outgas as deeper layers of the nucleus are heated. Time series photometry will determine whether the brightness variations stabilize into a periodic pattern, consistent with rotation, or remain erratic, suggesting something more complex. The object's trajectory will bring it within gravitational influence of Jupiter in late 2025. This encounter will not dramatically alter the orbit. 3I Atlas will pass at a safe distance, but the perturbation will be measurable. The magnitude of that perturbation depends on the object's mass, and any deviation from the predicted perturbation will constrain estimates of density and internal structure. Ground-based observatories are already coordinating observation campaigns. Time has been allocated on major telescopes. Imaging sequences are planned to capture rotation periods. Spectroscopic monitoring will track compositional changes. Radar observations are being considered, if the object passes within range of planetary radar systems, to directly measure the nucleus size and surface roughness. Space-based assets, Hubble, GJUST, and potentially others, will continue to provide high-resolution data, free from atmospheric distortion, capturing details invisible to ground-based instruments. Amateur networks will supplement professional observations, filling gaps in temporal coverage and providing redundancy against weather and scheduling conflicts. Each observation carries with it a prediction. If the object brightens at a certain rate, one model is supported. If the tail orientation shifts in a specific way, another is favored. If spectroscopic features appear or disappear, constraints tighten. The data will not provide answers immediately, but it will discriminate, progressively ruling out possibilities until only a narrower set of explanations remain. There is a discipline in not knowing, a rigor in acknowledging the limits of measurement and model, and resisting the instinct to force coherence where the data resists it. 3. Atlas is not the first object to challenge expectations. It will not be the last. The history of astronomy is filled with observations that did not fit, with anomalies that persisted until instrumentation improved or theory advanced enough to resolve them. Sometimes the resolution was mundane, a calibration error, an overlooked systematic, a misidentification. Other times, it was profound, a new class of object, a previously unrecognized physical process, a boundary condition that required theory to expand. The value of an object like this lies not in the immediate answer it provides, but in the pressure it places on understanding. It forces reconsideration. It exposes assumptions. It demands that models be tested against edge cases, where simplifications break down and the full complexity of nature asserts itself. Interstellar objects are rare. They pass through quickly, offering only a brief window for study before departing into the void. Oumuamua came and went before more than a handful of telescopes could observe it. Borisov, the second interstellar visitor, was a comet, active, bright, more cooperative with expectation, but still it left questions unanswered. 3I Atlas is the third data point, and with each new visitor, the statistical sample grows slowly, painstakingly, toward the threshold where patterns can be discerned and generalizations can be made. But for now, the data is incomplete. The behavior resists simple categorization. The object drifts through the solar system, indifferent to the telescopes trained upon it, to the models struggling to account for its motion, to the questions it raises simply by existing. And that is enough. That is what science is built to handle, not the certainty of answers, but the discipline of continuing to ask, to measure, to refine, to remain open to the possibility that what we are seeing is not an error in the data, but a signal we are only beginning to learn how to read. So the observation continues. The instruments remain trained. The campaigns are planned. The predictions are logged. The data is archived. And somewhere beyond Neptune, 3I Atlas continues inward, carrying with it a mystery that refuses, for now, to resolve.